Pick up a glass of water. You have done this 10,000 times. You will do it 10,000 more. There is nothing about it that asks for your attention. It is transparent. It is cold. It sits in your hand the way familiar things do, without weight, without mystery, without any signal that something unusual is happening. But something unusual is happening. The water in that glass has a history, not the history of the pipe it came through, or the reservoir it sat in, or the river that fed the reservoir. A history so much older than any of those things that those things do not even register as a rounding error on the timeline. Some of what you are holding may have formed before this planet existed, not arrived here before this planet existed. Formed, assembled from its component parts in the cold dark of a molecular cloud. Billions of years before the sun was a sun. Before Earth was anything more than a loose collection of dust and rock drifting in an unfinished solar system. You are holding something ancient, in a way the word ancient was not built to describe. And here is the thing that makes this more than a curiosity. Earth should not have this water. The planet formed in the wrong place, under the wrong conditions, at the wrong temperature, to hold on to volatile molecules like water. Every model of planetary formation that scientists have built says the same thing. A rocky planet at Earth's distance from a young star should be dry, should have lost its water to the heat before it ever had a chance to keep it. And yet, here you are, holding a glass of it. How that happened, what it took, what it cost, and what it means is one of the most interesting questions in all of science. It is also the story of almost everything. Put the glass down. We are going back a long way. 4.5 billion years ago, there was no Earth. There was a star, young and unstable and burning hotter than it burns today, surrounded by a disk of gas and dust that stretched outward for billions of miles in every direction. That disk was the raw material of everything in this solar system. Every planet, every moon, every asteroid and comet and grain of interplanetary dust that exists today was assembled from what was in that disk. But the disk was not uniform. It had a structure, and that structure determined everything. Close to the young sun, temperatures were extreme, high enough to vaporize ice, high enough to drive off volatile compounds before they could bind to the rocky material clumping together to form planets. The material in this inner zone was dry. Silicates, iron, nickel, the kinds of things that do not mind heat, that hold their form at temperatures that would strip a water molecule apart and send its components drifting into space, further out, beyond a boundary that planetary scientists call the snow line. Things were different. Out there, far enough from the sun that temperatures dropped to the point where ice could survive. The building material was richer, better. Volatile compounds could exist in solid form, could stick to rocky particles. It could accumulate into objects that were not just rock, but rock and ice and frozen gases, all bound together. The snow line was not a wall. It was a temperature boundary. And like all temperature boundaries in nature, it was fuzzy at the edges, shifting over time as the young sun's output changed, as the disk evolved, as the dynamics of a forming solar system rearranged the distribution of heat and matter. But it was real, and its basic logic was absolute inside it. Dry, outside it. Wet, Earth formed inside it. Not slightly inside, comfortably inside. At a distance from the sun, where the temperatures during the period of planetary formation were high enough to ensure that any water trying to stick to the material building this planet would have been cooked off long before it had a chance to stay. The models are clear on this. The building blocks that assembled into Earth, the small rocky bodies called planetesimals that crashed into each other over millions of years until they accumulated enough mass to become a planet, were formed in a region where water simply could not have been a major ingredient. The physics did not allow it. The temperature was wrong. The distance was wrong. Earth should have been born dry. This is the fact that everything else in this story has to contend with, not as background, as the central problem. Because if you want to understand where the water in your glass came from, you first have to sit with the reality that by every reasonable expectation, that water should not be here at all. Think about what that means for a moment. The ocean covering 71% of this planet's surface. The water cycling endlessly through clouds and rain and rivers and ice caps and the bodies of every living thing. The water that makes up most of your blood, most of your brain, most of the fluid in every cell in your body right now. All of it, every drop, is matter that had no obvious right to be on this particular planet in this particular part of the solar system. And yet here it is. There is a word scientists use when they talk about this situation. They call it a delivery problem. Earth needed water from somewhere that was not Earth. The question is where that somewhere was, and how the delivery happened across hundreds of millions of miles of space, and how enough of it survived the journey and the violence of arriving to fill an ocean, or several oceans. Or maybe, if a different line of evidence turns out to be correct, the question is something else entirely. Maybe the delivery came from a direction nobody expected. Maybe the source was not out there at all. But before we get to that, we need to understand what Earth was like when it was new. Because the delivery problem is only half the story. The other half is what happened to anything that arrived. And what happened was not gentle. Forget everything you know about Earth. The oceans, the continents, the blue sky and the green land, and the thin, breathable shell of atmosphere that makes all of it possible. Forget the familiar picture of this planet from space. That pale blue dot that has become so iconic, it feels like the definition of what a planet is supposed to look like. 4.5 billion years ago, Earth looked nothing like that. What existed then was something closer to a nightmare. A ball of rock and metal so hot that its entire surface was molten. A global ocean of magma, thousands of miles deep, glowing red and orange and white in the darkness of the early solar system. No crust, no solid ground anywhere, no place for water to pool, even if water had been present, because the surface temperature was high enough to vaporize it instantly and send it screaming into the atmosphere as superheated steam before it had any chance to do anything useful. The heat came from everywhere at once. It came from the collisions. Earth did not form the way a snowball forms, gathering material gently and growing layer by layer. It formed through violence, through the repeated high-velocity impacts of smaller bodies that had themselves been assembling through collision over millions of years. Each impact released energy. The larger the impactor, the more energy, and in the final stages of planetary formation, when the bodies involved were not pebbles or boulders, but objects the size of small moons, the energy released was almost incomprehensible. The kinetic energy of a body 100 miles across hitting a growing proto-Earth at orbital velocity does not just make a crater, it melts things. It melts a lot of things. It melts enough things that the heat cannot escape fast enough to let the surface solidify before the next impact arrives. The heat also came from inside. As Earth grew, the weight of the material piling on top compressed the interior. Compression generates heat. And the interior of a forming rocky planet contains something else as well. A collection of radioactive isotopes left over from the nuclear processes that built the elements in dying stars long before our solar system existed. Those isotopes were decaying, releasing energy as they did, adding to the heat from below, even as the impacts added heat from above. Earth was cooking from both directions simultaneously. And then there was the differentiation. At some point during this molten period, something happened that would shape every aspect of this planet's future, including the story of its water. The heavy elements, primarily iron and nickel, began to sink toward the center. The lighter silicate materials floated toward the surface. Earth was separating itself into layers, a process called differentiation, and it was doing so in a way that released yet more energy as dense material fell inward through the molten rock, converting gravitational potential energy into heat, the way a falling object converts potential energy into the energy of impact. The differentiation also did something else, something that matters directly to the water story. As the iron sank to form the core, it did not sink alone. Iron has a chemical affinity for certain other elements that geochemists call siderophile, which means iron-loving. These elements tend to dissolve into molten iron and travel with it. And among the things traveling with the iron toward the core were a significant portion of any volatile compounds that had managed to survive the heat up to that point. The young Earth was not just hot enough to prevent water from surviving on its surface. It was actively pulling the chemical components of water down into a place from which they could not easily return. If you had been watching from a safe distance during this period, which would have required being very far away and having extraordinary patience, you would have seen a planet that seemed to be doing everything in its power to disqualify itself from ever supporting life. The surface was a sea of glowing rock, the sky above it, to the extent that a sky existed at all, was a thick blanket of vaporized silicates and volcanic gases, so hot and so dense that the sun would have been invisible through it. Anything as fragile as a water molecule that found itself in that environment would have lasted about as long as a snowflake in a furnace. And the solar wind was not helping. The young sun was more active than it is today, putting out a stronger flow of charged particles that stripped material from the upper atmosphere of any planet within range. Earth had not yet developed the strong magnetic field it has now, because the magnetic field is generated by the movement of the liquid outer core, and the core was still forming. Without a strong magnetic field, the solar wind reached deeper into the atmosphere, carrying off light elements, including hydrogen, the element you need to build a water molecule. Everything was working against this planet, keeping anything wet. The heat from above, the heat from below, the gravitational settling that pulled volatile materials toward the core, the solar wind stripping the atmosphere from outside, the violence of ongoing impacts that reset the surface conditions every time something large enough arrived. And yet something changed. Something always changes. Because planets are not static objects. They are systems. And systems evolve. And the direction of evolution, for a planet with enough mass in the right location and the right internal chemistry, is not always toward more chaos. Earth started to cool. Not quickly. Geological processes do not move at a pace that would be recognizable as fast by any human standard. But over millions of years, the rate of large impacts declined as the supply of large impactors in the inner solar system was depleted. The surface began to lose heat to space faster than new heat was being added. A thin crust started to form in places, solidifying at the top of the magma ocean the way a skin forms on cooling chocolate. The atmosphere, heavy and reducing, rich in carbon dioxide and nitrogen, and water vapor and gases released by constant volcanic activity began to develop something like a stable structure. Not breathable, not friendly, but present. And into this slowly cooling, still brutally violent world, something was about to happen that would reset every calculation. Something that would take the question of Earth's water and make it immeasurably more complicated and immeasurably more interesting. The sky was about to fall, not metaphorically, not as poetry, as a physical event of a scale that makes every other event in the history of this planet look like a footnote. Something was coming. Picture the largest thing you can imagine hitting this planet. Now make it bigger. Roughly 4.5 billion years ago, an object, approximately the size of Mars, was on a collision course with the young Earth. Not a near miss, not a grazing blow, a direct, catastrophic, full-scale planetary collision between two bodies that had both been accumulating mass for tens of millions of years, each one carrying within it the chemical inventory of its entire formation history. Scientists call this object Theia. The name comes from Greek mythology, from a titan whose daughter was the goddess of the moon. The naming was intentional, because the leading hypothesis for where our moon came from is that it was born from this collision, assembled from the debris that the impact blasted into orbit around the surviving Earth. But the moon is not the part of this story we are here for. The impact released energy on a scale that the word catastrophic does not begin to contain. The entire surface of Earth was remelted. The crust that had been slowly, painfully forming over tens of millions of years was obliterated. The atmosphere was blasted away. A significant portion of Earth's mantle was vaporized and thrown into space, where it began to coalesce into what would become the moon. Any water that had been present on or near Earth's surface before the impact would have had an extremely difficult time surviving it. But here is where the story refuses to give you the answer you expected. Theia was not an empty rock. Whatever it was made of, wherever it formed, it had spent tens of millions of years accumulating mass and building its own chemical inventory. Some dynamical models suggest Theia could have been a volatile-bearing body, one carrying carbon, nitrogen, and water-bearing material that the impact would have deposited directly into Earth's interior and lower atmosphere, not destroyed on arrival, but mixed in, incorporated, redistributed through the planet that absorbed it. The composition of Theia is not settled science, and different models place it in different parts of the early solar system with meaningfully different implications for what it carried. But the possibility itself matters because of what it means structurally for the story. The impact that melted Earth's surface and blew away its atmosphere may also have been one of the moments Earth first received what it needed to become a living world. Destruction and delivery, arriving simultaneously, indistinguishable from each other in the moment of impact. The moon, that formed from the debris, was, in its earliest days, much closer to Earth than it is now. The tidal forces it exerted were immense, driving enormous tidal heating in Earth's interior, keeping the mantle partially molten, sustaining the geological activity that would eventually stabilize this planet's long-term climate. The moon was not just a byproduct of the collision. It became, from the moment of its formation, one of the reasons Earth remained active enough to do what it needed to do. But Earth, after the collision, was back to something close to where it had started. A molten surface, a ravaged atmosphere, a volatile inventory that was uncertain at best, depleted at worst. The delivery problem had not been solved. If anything, it had been made more acute. And the solar system was not finished delivering things to the inner planets, not by a very long way. For most of the history of this science, the question was framed one way. Water arrived from somewhere out there, carried by something that crossed the vast distance between the wet outer solar system and the dry inner one and deposited its cargo on a planet that had none. The delivery model. The idea that Earth was a dry recipient and space was a wet supplier, and the story of our oceans is fundamentally a story of transport across hundreds of millions of miles. It is a reasonable framework. It fits the basic physics of where water can and cannot survive during planetary formation. It explains why we need to look outward for the origin of something so fundamental. But science has a way of making reasonable frameworks uncomfortable. And in the last decade, a quieter line of research has been building a case for something that changes the question entirely. What if the water was already here? Not here in the sense of sitting on the surface waiting to be found. Here in the sense of locked inside the very material that built this planet. Hidden in chemical bonds, within minerals that do not look wet, that would not feel wet, that would pass every casual inspection as ordinary dry rock. Hydrogen bound to silicate structures at the molecular level, stored in a form that requires specific conditions to release, waiting inside the building blocks of Earth itself for the moment those conditions arrived. The specific rocks at the center of this argument are called enstatite chondrites. They are among the most primitive objects we have access to in the solar system, remnants of the earliest solid material that formed in the disk around the young sun. What makes them particularly relevant to Earth is their isotopic composition. When geochemists compare the isotopic signatures of Earth's mantle with various classes of meteorites, the enstatite chondrites match better than almost anything else. They are, by the best current evidence, the closest thing we have to the actual building material of this planet, the stuff Earth was made from. For a long time, enstatite chondrites were considered dry, formed close to the sun. In the hot inner disk, they should not have retained significant quantities of hydrogen. The assumption was that whatever hydrogen they started with was lost during the high-temperature conditions of their formation. Then a team of researchers looked more carefully. A study published in 2025 analyzed an enstatite chondrite called La-12-252, recovered from Antarctica, using techniques sensitive enough to detect hydrogen bound within the mineral structure at concentrations that earlier methods would have missed. What they found was that this class of meteorite contained significantly more hydrogen than anyone had assumed, stored not as water, not as ice, but as hydrogen atoms sitting within the crystal lattice of the minerals themselves, bound tightly enough to survive the conditions of formation, but available to be released through geological processes, through heat and pressure and the chemistry of a differentiating planet. The implications are quiet but significant. If the building blocks of Earth contained hydrogen at these concentrations, then Earth did not form dry and wait for a delivery. Earth formed with the ingredients for water distributed throughout its interior. The oceans, on this reading, are not imported goods. They are a domestic product, the result of geological processes releasing hydrogen that was built into this planet from the very beginning, combining it with oxygen through the chemistry of a cooling, outgassing world. This does not mean the delivery model is wrong. The two ideas are not mutually exclusive, and most researchers working in this area believe the truth is some combination of both, that Earth had internal sources of hydrogen and also received external contributions from impacting objects over hundreds of millions of years. The question of proportion, how much came from inside and how much came from outside, is still genuinely open. But the existence of the internal source changes the shape of the mystery. It means the question is not simply where Earth got its water. It means the question is how a planet that was born with the right ingredients, then subjected to conditions almost perfectly designed to destroy those ingredients, still managed to hold on to enough of them to fill an ocean. That is a different question, a harder question, and in some ways a more interesting one, because it means the story of Earth's water is not the story of a lucky delivery from a generous universe. It is the story of a planet fighting to keep something it already had. Think about what that fight looked like. Hydrogen trapped in mineral structures, surviving the heat of planetary formation, surviving the violence of late-stage accretion, surviving the differentiation event that pulled iron toward the core and dragged volatile elements with it. Somehow, not all of it went down with the iron. Somehow, enough remained in the mantle and in the material arriving from outside to eventually work its way to the surface through volcanic outgassing, through the slow release of gases from the interior that built the early atmosphere, one volcanic eruption at a time. The first water on Earth's surface may not have rained down from the sky. It may have come up from the ground, exhaled by a planet that had been holding its breath since before it had a surface to breathe from. There is something worth sitting with in that image. The idea that the water you drink did not have to travel across the solar system to get here, that it may have been inside this planet, waiting through the magma ocean and the impacts and the differentiation and all of it, for the moment conditions finally allowed it to reach the surface and stay. Maybe Earth was never waiting for water to arrive. Maybe it was just waiting for the right moment to let what it already had come out. Every detective story needs a method. You can have a crime scene. You can have suspects. You can have competing theories about what happened and who was responsible and in what order the events unfolded. But without a way to test those theories against physical evidence, you have nothing but stories, reasonable stories, maybe internally consistent stories, but stories without the ability to eliminate alternatives, which means stories without the ability to get closer to what actually happened. The scientists investigating the origin of Earth's water have a method. It is elegant in the way that the best scientific tools tend to be, simple in its logic and surprisingly powerful in its application. And once you understand it, you will never look at a glass of water quite the same way. Hydrogen has a secret. Most hydrogen atoms are simple. One proton, one electron, the lightest and most abundant element in the universe, assembled in the first minutes after the Big Bang and scattered through everything that has existed since. This is the hydrogen in water, the hydrogen in your body, the hydrogen in the sun. But some hydrogen atoms are heavier. They have one proton and one neutron in their nucleus instead of just a proton, which makes them roughly twice the mass of ordinary hydrogen. This heavier version is called deuterium. It is not radioactive. It does not decay into something else. It just sits there, being heavier, behaving slightly differently in chemical reactions because of that extra mass. Deuterium exists in a specific ratio to ordinary hydrogen in any given sample of water, and that ratio is not the same everywhere in the solar system. The reason for this is temperature. In the cold outer regions of the solar system, far from the sun, chemical reactions that preferentially incorporate deuterium over ordinary hydrogen are more favorable. Objects that formed in the cold outer disk, comets and carbonaceous asteroids and icy bodies beyond the snowline, tend to have higher deuterium to hydrogen ratios than objects that formed closer to the sun in warmer conditions. This means the ratio is a fingerprint, a record of where a body of water has been or more precisely, where the material containing it originally formed. When scientists measure the deuterium to hydrogen ratio in Earth's oceans and compare it to the ratio in various meteorites and comets, they are not just doing chemistry. They are asking those objects where they came from. And the answers, while not always clean, are telling. The carbonaceous chondrites, a class of meteorite that formed in the outer asteroid belt, tend to have deuterium to hydrogen ratios that come reasonably close to Earth's ocean water. Not a perfect match, close enough to suggest a meaningful contribution. Close enough that for several decades, carbonaceous asteroids were considered the most likely primary source of Earth's water. Then there is the meteorite that fell in Australia in the early morning hours of September 28, 1969. The Murchison meteorite landed near the town of Murchison in Victoria, scattering fragments across a wide area of farmland. It weighed over 100 kilograms in total, making it one of the largest carbonaceous chondrite falls ever recovered. Researchers collected samples within days and began analyzing them. What they found inside that rock changed the conversation about the chemistry of space permanently. Murchison contained water, bound within its mineral structure. The same way the enstatite chondrites discussed in the last chapter contain hydrogen, but in greater abundance and in a form that was clearly connected to the outer solar system's wet chemistry. It contained amino acids, more than 70 different types, including many of the same ones that living things on Earth use to build proteins. It contained sugars. It contained nucleobases, the molecular components of DNA and RNA, all of it formed in space, by purely chemical processes, with no biology involved at all. The year 1969 is worth pausing on. In the summer of that year, 12 days before Murchison fell, Neil Armstrong stepped onto the surface of the moon and picked up rocks that had been sitting undisturbed since the solar system was young. Rocks that would tell scientists about the violence of early bombardment, about the age of lunar basins, about the history of the inner solar system in the period when water was arriving or not arriving on young planets. And then, 12 days later, a rock arrived from space without any human assistance, a carbonaceous chondrite carrying its own archive of early solar system chemistry, landing in a field in Australia as if to provide the other half of the answer. The same year, both halves of the same story. Murchison was not a unique object. It was a sample from a class of material that exists throughout the asteroid belt, that has been hitting Earth regularly since the planet formed, that represents one of the most chemically complex natural objects we have access to. Its deuterium to hydrogen ratio falls within the range of Earth's ocean water. Not an exact match, a range. And this is where the fingerprint evidence gets genuinely complicated, because the comets do not cooperate. For a long time, the intuitive answer to the water delivery problem was comets. They are, after all, essentially dirty snowballs, bodies made largely of ice that formed in the cold outer solar system, exactly where you would expect water to be abundant. They cross the inner solar system. They hit planets. They should be delivering water to everything in their path. The deuterium to hydrogen ratio in comets tells a different story. When the European Space Agency's Rosetta mission reached Comet 67P, Churyumov-Gerasimenko, in 2014 and measured the water in its coma, the deuterium to hydrogen ratio came back at roughly 3 times higher than Earth's ocean water. 3 times. That is not a close match. That is a fundamental mismatch that calls into question whether comets of this type could have been the primary source of Earth's water. Earlier measurements of other comets had shown similar results, with a few exceptions. Comet Hartley 2, measured by the Epoxy mission, showed a ratio much closer to Earth's oceans. But Hartley, too, belongs to a different population of comets than 67P, and the sample size is small enough that drawing broad conclusions is difficult. The picture that emerges from all this measurement is not a clean one. The fingerprints point in multiple directions. Carbonaceous asteroids are a strong candidate for the primary delivery vehicle. Comets may have contributed something, but probably not as the dominant source. And the internal hydrogen described in the previous chapter may represent yet another pathway that operated in parallel. The honest summary of where the isotope evidence stands today is this: Earth's water does not have a single address of origin. It has several, and the question of how much came from each source, in what proportions, and at what times, is a problem that the best geochemists in the world are still actively working on, which means the investigation is not over. The fingerprints are there. Reading them correctly is turning out to be harder than finding them. But harder is not the same as impossible. And what the fingerprints have already told us, even in their ambiguity, is enough to rule out the simplest versions of the delivery story and point towards something more complex. Something that was not a single event. Something that happened over hundreds of millions of years, through multiple mechanisms, driven by the same solar system dynamics that were simultaneously building planets and destroying them and rearranging everything in between. The delivery, it turns out, was not a delivery at all. It was a process, and that process was about to reach its most violent and consequential phase. There is a version of this story that is almost perfect. It has everything a good scientific narrative is supposed to have: a clear mechanism, an obvious source, a logical chain of cause and effect that moves from problem to solution without unnecessary complexity. It is the kind of answer that, when you first hear it, makes you nod and think yes. Of course, that makes sense. Why would it be anything else? For decades, that answer was comets. Think about what comets are and where they come from, and the logic becomes hard to resist. They are ancient objects, assembled in the cold outer reaches of the solar system, where temperatures never rose high enough to drive off volatile compounds. They are made largely of ice, water ice, carbon dioxide ice, carbon monoxide ice, mixed with rocky and organic material in proportions that make them some of the most chemically complex natural objects in the solar system. They travel in long elliptical orbits that bring them swinging through the inner solar system, crossing the paths of the rocky planets, sometimes hitting them. A young Earth, dry and hot, and sitting in the wrong part of the solar system to have gathered water on its own, would have been a target for every comet that crossed its orbit. And in the early solar system, there were many more of them than there are today. The gravitational dynamics of the outer solar system were still evolving, still throwing objects into new trajectories, still sending material that it had formed far from the sun on journeys inward. The picture was coherent, elegant, even. Comets formed in the wet outer solar system. Comets hit the dry inner solar system. Earth got its oceans. The distance between the problem and the solution was exactly the distance between the snowline and Earth's orbit, covered by objects that were essentially flying packages of frozen water. Scientists built models around this. Textbooks described it. Documentaries illustrated it with comets streaking across early Earth's sky, their ice vaporizing on impact and adding to the growing ocean below. It became, for a generation of people learning about planetary science, simply the way it worked. Then, the measurements started coming in. The first serious challenge came from the deuterium to hydrogen ratio. As the previous chapter described, this ratio is a chemical fingerprint that records the temperature conditions under which water formed. Objects that formed far from the sun in cold environments tend to have high deuterium to hydrogen ratios. Earth's oceans have a specific ratio that can be measured with great precision. When scientists measured the deuterium to hydrogen ratio in comets, the numbers did not fit. The earliest careful measurements, conducted on comets like Halley, Hyakutake, and Hale-Bopp throughout the 1980s and 1990s, showed deuterium to hydrogen ratios roughly 2 to 3 times higher than Earth's ocean water. 2 to 3 times. In isotope geochemistry, that is not a close match. With measurement uncertainty, that is a fundamental chemical difference, suggesting these objects and Earth's water formed under significantly different conditions. The comet theory did not collapse overnight. Science rarely works that cleanly. Researchers looked for explanations. Maybe the comets that hit early Earth were different from the comets being measured today. Maybe the delivery involved different populations of comets from different parts of the outer solar system. Maybe the measured comets were not representative of the full range of cometary compositions. These were reasonable responses. They kept the theory alive while the evidence continued to accumulate. Then came Rosetta. The European Space Agency launched the Rosetta spacecraft in 2004 with the specific goal of rendezvousing with a comet and studying it in unprecedented detail. After a 10-year journey, Rosetta reached Comet 67P Churyumov-Gerasimenko in 2014 and began one of the most thorough investigations of a cometary body ever attempted. The spacecraft orbited the comet for over 2 years, measuring its composition, mapping its surface, watching it change as it moved closer to the sun. The deuterium to hydrogen ratio in the water vapor, coming off 67P, came back at approximately 3 times Earth's ocean value. 3 times. This was not a measurement of a distant comet inferred from light curves and spectroscopy. This was a direct measurement from a spacecraft sitting alongside the comet, sampling the actual water molecules released from its surface. The precision was high. The result was robust. 67P could not have been the primary source of Earth's water. The announcement landed with a particular weight in the planetary science community because 67P belongs to the Jupiter family comets, objects whose orbits are controlled by Jupiter's gravity and that are thought to represent one of the most likely populations to have delivered material to the early inner solar system. If Jupiter family comets had the wrong ratio, the most accessible and dynamically plausible population of comets was essentially ruled out as the dominant source. But then, something happened that illustrates why following this story requires holding multiple ideas in tension simultaneously. Subsequent analysis of the Rosetta data found that the measurement was more complicated than initially understood. The deuterium to hydrogen ratio in the vapor coming off the comet's surface varied depending on which part of the surface it came from and what season it was on the comet. The dust-rich regions gave different readings than the ice-rich regions. The interaction between solar radiation and the comet's surface was affecting the composition of what was being measured in ways that were not fully accounted for in the initial analysis. This did not restore comets to their previous standing. The basic problem with the ratio remained, but it added nuance to what the measurement actually meant. And it served as a reminder that reading the fingerprints of objects 4.5 billion years old from the signals they emit today is not a straightforward exercise. The exception case made things more interesting still. Comet Hartley 2, measured by the NASA Epoxy mission in 2010, showed a deuterium to hydrogen ratio much closer to Earth's oceans. Hartley 2 is a different kind of comet than 67P, belonging to a population that may have originated in the Kuiper belt rather than the scattered disk. If different populations of comets have different ratios, then perhaps some fraction of Earth's water came from comets of the Hartley 2 variety. Even if the dominant Jupiter family comets were not the primary source, the picture that emerges from all of this is messier than the elegant original theory. Some comets match. Most do not. The ones that match are less dynamically likely to have hit early Earth in large numbers. The ones that do not match are more dynamically plausible but chemically wrong. There is a sentence that belongs somewhere in every honest account of the comet theory. Comets were the most beautiful answer to the water delivery problem. And the universe, it turns out, does not grade on beauty. What the isotope evidence has done, taken together across all the measurements, from all the missions and all the meteorite analyses and all the careful work in laboratories around the world, is to point toward carbonaceous asteroids as the more likely dominant source of delivered water, while leaving open a role for comets, while simultaneously raising the possibility that internal sources of hydrogen contributed significantly, while acknowledging that Theia and other large impactors may have played a role, while noting that the proportions of all of these contributions remain genuinely uncertain. This is not a satisfying answer. It does not fit on a diagram with a clean arrow pointing from source to destination. It is the kind of answer that frustrates people who want science to behave like a locked room mystery, where the detective assembles everyone in the drawing room and names the single guilty party. But it is the honest answer, and there is something in the honesty itself that is more interesting than the elegant theory it replaced. Because what it means is that Earth did not get lucky once. Earth did not receive one decisive delivery at one pivotal moment that solved the water problem cleanly and permanently. Earth gathered water the way it gathered everything else, incrementally, from multiple sources, over an almost incomprehensibly long period of time, through processes that were not designed to deliver water, but that happened to do so as a consequence of the same dynamics that were building and reshaping the entire solar system. Water was not a gift. It was an accumulation, and the period during which the most significant accumulation happened was approaching. There is a photograph taken in 1969 that most people have seen without knowing what they were looking at. It is a photograph of the moon's surface, not the dramatic shot of Armstrong's boot print, not the iconic Earthrise image from Apollo 8. This one is less famous. It shows a landscape that looks, at first glance, like a gentle rolling terrain, softly lit, almost peaceful in its stillness. Look more carefully, and you see that every surface, every hill and every valley and every flat plain in the image is covered in craters, small craters inside larger craters, overlapping craters, a landscape so thoroughly impacted that there is almost no original surface left, just the accumulated record of billions of years of things hitting it. That photograph is one of the most important documents in the history of planetary science, because what it shows is not just the moon's past, it shows Earth's past. Earth and the moon occupy essentially the same position in the solar system. They have been together for 4.5 billion years. Since the Theia impact assembled the moon from Earth's own material, whatever hit the moon during that time also hit Earth, in roughly comparable proportions, adjusted for the difference in size and gravitational cross-section. The moon received every impact it ever sustained and kept the record perfectly, because it has no erosion, no plate tectonics, no water, no atmosphere, no mechanism of any kind for erasing what was done to it. Earth received the same bombardment and erased almost all of it. The cratered lunar surface is, in a very real sense, a mirror showing us what Earth looked like before it learned to heal itself. The period we are concerned with here is called the Late Heavy Bombardment. Though that name comes with an asterisk, that will become important. The Apollo rock samples, brought back from 6 lunar landing sites between 1969 and 1972, showed something unexpected when scientists dated the impact melts. The glassy rocks formed by the intense heat of large collisions, the dates clustered. Instead of being spread evenly across 4.5 billion years, the major basin-forming impacts on the Moon appeared to have occurred within a relatively narrow window, roughly between 4 billion, 100 million, and 3 billion, 800 million years ago. This suggested that the bombardment was not a steady rain that gradually declined over time. It had a pulse, a concentrated spike of violence in a relatively short geological window, after a period of comparative quiet. If that spike was real, and the debate about its exact nature continues among planetary scientists, then the inner solar system experienced something extraordinary in that window, a concentrated delivery of material from the outer solar system, driven by the gravitational instabilities described in the NICE model, where the orbital migration of the giant planets destabilized the reservoir of small bodies beyond them and sent a significant fraction of that material raining inward. The implications for water are direct. The objects in that outer reservoir were not the same as the rocky bodies of the inner asteroid belt. They formed beyond the snowline. They contained ice. They contained volatile compounds. They were, in the terminology of the previous chapters, exactly the kind of material that the dry inner solar system needed, and they were arriving in quantities and at frequencies that are difficult to overstate. Every large impact during this period was simultaneously a destructive event and a delivery event. The same object that excavated a basin hundreds of miles across, that melted rock and threw debris into the upper atmosphere and disrupted whatever fragile conditions were trying to establish themselves on the surface, also deposited its own chemical inventory into the Earth system. Its water, its carbon, its nitrogen, its organic compounds, mixed into the impact melt, incorporated into the cooling rock, gradually worked into the atmosphere and the early ocean through the geological processes that followed. Destruction and delivery, as discussed in the chapter on Theia, arriving together, not as a paradox, as a physical reality. But here is where the bombardment story intersects with the survival story in the most important way. Earth was not alone in receiving this bombardment. Mars received it. Venus received it. The Moon received it. As the photographs make clear, every rocky body in the inner solar system was hit during this period by material from the outer solar system. Every one of them received a delivery of volatile rich material. The water problem was not unique to Earth. What was unique to Earth was what happened next. Mars received water. We know this because Mars has valley networks carved by liquid water, ancient lake beds, minerals that only form in the presence of water. A geological record that speaks clearly of a planet that was once significantly wetter than it is today. Mars received the same delivery. Mars could not keep it. Venus may have had liquid water early in its history. Some models suggest it did, for a period of perhaps several 100 million to 1 billion years, before the runaway greenhouse effect that defines Venus today took hold and drove every drop of water off the surface and eventually out of the atmosphere entirely. Venus received the delivery. Venus lost it to a different kind of catastrophe. The Moon has water ice today, hiding in permanently shadowed craters near the poles where sunlight never reaches. But the Moon has no liquid water, no ocean, no hydrological cycle, no mechanism for using the water. it has to do anything except sit frozen in the dark. The moon received the delivery. The moon could not do anything with it. Earth kept its water, and the reason Earth kept its water comes down to a set of characteristics that are, individually, not unusual. Together, they are everything. Size is the first factor. Earth is large enough that its gravity holds onto a substantial atmosphere. A thin atmosphere bleeds away over geological time under the pressure of the solar wind. A thick enough atmosphere, maintained by ongoing volcanic outgassing from a geologically active interior, creates a buffer that slows the loss of volatile compounds to space. Mars, with roughly 1/10 of Earth's mass, could not maintain a thick enough atmosphere. The solar wind thinned it over billions of years until the pressure was too low to keep water liquid on the surface. The magnetic field is the second factor. Earth's liquid outer core generates a global magnetic field that deflects the solar wind before it reaches the upper atmosphere. Without that deflection, the solar wind strips hydrogen from water molecules in the upper atmosphere, gradually depleting the planet's water inventory. Mars lost its magnetic field when its smaller core cooled and solidified, probably within the first billion years of its history. After that, the solar wind had direct access to the Martian atmosphere. Plate tectonics is the third factor, and in some ways, the most important. The movement of tectonic plates drives a long-term cycle that regulates Earth's climate over geological timescales. Carbon dioxide, a greenhouse gas, is released by volcanoes and drawn down by chemical weathering of rocks. When the climate warms, weathering accelerates, drawing down more carbon dioxide. Cooling the climate. When the climate cools, weathering slows, allowing carbon dioxide to build up, warming the climate again. This thermostat, powered by plate tectonics, has kept Earth's surface temperature within the range where liquid water can exist for most of 4 billion years. Venus has no plate tectonics. Its surface is periodically resurfaced by massive volcanic episodes. But without the continuous cycling of material through subduction zones, the carbon cycle thermostat does not operate. Carbon dioxide accumulates without a mechanism to draw it down. The greenhouse effect intensifies. Temperatures rise. Water evaporates. The feedback loop has no internal break. Earth sat in the right place, with the right size, with the right internal heat to sustain a magnetic field and plate tectonics for long enough to keep a cycle running that nothing in the inner solar system except Earth has managed to sustain. The delivery mattered. But the delivery was not enough. What mattered, in the end, was not how much water arrived. It was whether the planet receiving it had the architecture to hold on to it, to cycle it, to keep it moving between the ocean and the atmosphere and the rock and the ocean again, in a loop that has been running without interruption for nearly 4 billion years. Earth did not receive water. Earth earned it, in the sense that it had exactly the properties needed to keep what it got, while everything around it either lost its share to space, or locked it in ice, or boiled it off into a runaway greenhouse. There is a sentence that belongs at the end of this part of the story, not as a conclusion but as a transition, because the story does not end with the delivery. The delivery was the beginning. What water did after it arrived, what it became, what it made possible, is a different story, quieter than the bombardment, less dramatic than planetary collisions, but more consequential than any of it, because water, once it was here, did not sit still. There is a crystal in a laboratory in Western Australia that is older than almost anything you will ever encounter. It is small, smaller than a grain of sand, You could lose it between the fibers of a piece of cloth without trying. It has no remarkable color, no visual quality that would stop you if you passed it on a table without knowing what it was. It is a grain of zircon, pulled from a rock formation called Jack Hills, and it is 4,400,000,000 years old. To put that number in terms a human mind can actually hold, when this crystal formed, the sun had been burning for only about 100 million years. The solar system was new in a way that the word new cannot fully carry. The Theia impact had happened relatively recently on geological timescales. The surface of Earth was still largely molten, still being shaped by impacts, still figuring out what it was going to be. And yet inside this crystal, locked into the chemistry of its oxygen atoms, is a signature that stopped scientists cold when they first recognized what they were seeing. The signature of liquid water. Not an ocean, not a sea, but water. Actual liquid water, touching the surface of a planet 4,400,000,000 years ago. At a time when every assumption about early Earth said the surface should have been nothing but molten rock and chaos. The oxygen isotope ratios in the Jack Hills zircon are consistent with the crystal having formed in the presence of liquid water, in a relatively cool environment, at temperatures far below what anyone expected to find evidence of this early in Earth's history. That crystal changed the story. For a long time, the narrative of early Earth was built around an image of unrelenting hostility, the Hadean Aeon, named after Hades. The Greek underworld was conceived as a period of continuous hellish conditions, lasting from Earth's formation until roughly 4 billion years ago. Nothing could survive it. Nothing interesting could happen during it. Life, obviously, had to wait until it was over. The Jack Hills zircon complicated that picture, and the complication pointed toward something that the science has been slowly building a case for over the past 2 decades. The early Earth, even during the Hadean, may have had windows. Not long ones, not stable ones, not the kind of windows that would let you stand outside without dying in several different ways simultaneously, but windows of relative coolness, windows where liquid water could exist on at least parts of the surface. Windows that opened between the catastrophic impact events and closed again when the next large impactor arrived. The surface of early Earth was not a steady state of maximum hostility. It was a fluctuating environment, sometimes catastrophically hot, and sometimes, in the intervals between major impacts, closer to conditions where chemistry could begin to organize itself into something more interesting. But before there were windows, there was the cooling. After the Theia impact, after the moon had assembled from the debris cloud, and the surviving Earth had begun to differentiate into its layered structure, the planet started the long, slow process of losing heat. Not steadily, not gracefully, but persistently, over millions of years, radiating energy into space. The rate of large impacts declining as the supply of large impactors was gradually depleted. The magma ocean cooled from the top down. The surface, exposed to the cold of space, lost heat fastest. A thin crust of solidified rock began to form, cracking and remelting and reforming as volcanic activity from below constantly disrupted it, but gradually thickening in the intervals between disruptions. Beneath this thin crust, the interior was still largely molten, convecting vigorously, driving volcanic activity that was far more intense than anything Earth experiences today. Every volcanic eruption released gases from the interior into the atmosphere, a process called outgassing, and among those gases was water vapor. This is a critical point that is easy to miss. The water vapor entering the early atmosphere did not come only from impacting objects delivering their cargo on arrival. It also came from the planet itself, from the interior, from the hydrogen that had been locked in mineral structures since the planet formed, from whatever volatile material had survived differentiation and remained in the mantle, being carried upward by magma and released into the atmosphere through volcanic vents. The early atmosphere was thick with it. Water vapor mixed with carbon dioxide, nitrogen, sulfur dioxide, and the other gases of a geologically hyperactive planet, creating a dense greenhouse blanket that trapped heat and kept surface temperatures elevated even as the sun, which was about 30% fainter then than it is today, would not have been able to do the job alone. High temperatures and high water vapor content in the atmosphere are not conditions under which rain falls and stays on the surface. They are conditions under which rain falls and immediately evaporates. The way water dropped onto a very hot pan does not sit still, but immediately converts to steam and rises again. The early water cycle, to the extent that it existed at all, was a furious loop of evaporation and condensation, with no stable reservoir at the bottom. And then, slowly, the balance began to shift. As the rate of large impacts declined, the rate of heat input to the surface declined with it. The crust thickened. The intense early volcanism moderated slightly. The atmosphere began to cool from the top, and as it cooled, the water vapor in it began to condense more efficiently. The first real rain fell on rock that was still warm enough to send it straight back into the sky. Then it fell again, and again, each cycle carrying heat upward and releasing it to space, cooling the surface by a fraction of a degree, cooling the atmosphere by a fraction of a degree, pushing conditions incrementally toward the threshold where water could stay. This may not have been a single rainstorm. It may not have been a single period of years or decades. It may have been an episodic process that happened, was interrupted by large impacts that reset surface conditions, and then happened again, and was interrupted again, and happened again. The geological record from this period is almost entirely absent, erased by 4 billion years of the very geological activity that makes Earth the kind of planet that can have a geological record worth reading in the first place. What the Jack Hill zircon tells us is that by 4,400,000,000 years ago, the process had reached a stable enough stage that liquid water was present. Not everywhere, not continuously, but present, touching rock, participating in chemistry, beginning the long career that would define this planet. Nobody was there to see the first rain. There was no surface to stand on. Not safely. The sky above would have been unrecognizable, thick and orange and lit from below by the glow of volcanic activity visible over every horizon. The sun, smaller and fainter than the one you know, would have been invisible through the haze. The rain itself would not have looked like rain as you know it. It would have been hot, acidic, laden with dissolved gases from the atmosphere it fell through, hitting rock that was itself warm enough to steam on contact. It would not have been beautiful in any way you would recognize, but it was rain, water falling from sky to ground, the first installment of a process that has been running without full interruption since before the oldest rock on Earth was formed. A process that has moved every water molecule on this planet through the cycle of evaporation and condensation and precipitation and runoff and evaporation again, over and over, for nearly 4 billion years. The zircon crystal is the only witness we have. 4,400,000,000 years old, smaller than a grain of sand, found in a rock outcrop in the middle of Australia by geologists who were looking for something else entirely, carrying in its oxygen isotopes the chemical memory of a moment when water first touched the surface of this planet and the surface was cool enough, just barely, to let it stay. Nobody was there when the first rain fell, but it left its signature in a crystal smaller than anything you can see without a microscope. And 4 billion years later, we found it. Stop thinking about water as a liquid. You have been thinking about it that way throughout this story, and reasonably so. The question has been where it came from, how it survived, how it arrived on a dry planet, how the first rain fell on cooling rock. Water as substance, water as cargo, water as the thing that had to get here before anything else could happen. Now, think about what it is. A molecule of 2 hydrogen atoms bonded to 1 oxygen atom, H2O. Simple enough that a child can write the formula. So simple that it is almost impossible to believe it is the reason this planet is alive. Except that is not quite what it is. And the difference between the formula and the reality is the difference between a map and the territory it describes. The water molecule is bent. The 2 hydrogen atoms do not attach to the oxygen in a straight line. They attach at an angle, roughly 104 degrees, in a shape that gives the molecule an uneven distribution of electrical charge. The oxygen end of the molecule carries a slight negative charge. The hydrogen ends carry a slight positive charge. This makes water a polar molecule, meaning it has a permanent electrical asymmetry built into its structure at the quantum mechanical level. That asymmetry is responsible for almost everything. Because of it, water molecules are attracted to each other in a specific way. The positive hydrogen end of one molecule pulls toward the negative oxygen end of a neighboring molecule, forming what chemists call a hydrogen bond. Each water molecule can form up to 4 of these bonds simultaneously, creating a dynamic, constantly rearranging network of connections that gives liquid water properties unlike almost any other substance at the temperatures where life operates. Take the most counterintuitive of those properties first. Ice floats. This seems trivial. It is not. In almost every other substance in nature, the solid form is denser than the liquid form. When a substance freezes, its molecules pack more tightly together, and the solid sinks. Water does the opposite. When water freezes, the hydrogen bonds arrange the molecules into a crystalline lattice that is actually less dense than the liquid, which is why ice cubes float in your glass and icebergs float in the ocean. The consequence of this single physical quirk for the history of life on Earth is enormous. If ice sank, lakes and oceans would freeze from the bottom up. Once the bottom froze, the overlying water would be cut off from the geothermal heat of the sediment below. The ice layer would grow upward and outward until the entire body of water was solid. The only thing preventing this from happening to every body of water on Earth during the ice ages that have punctuated this planet's history is the fact that the ice stays at the surface, where it can be melted by solar radiation, where it insulates the liquid water below, where it keeps the deep ocean liquid even when the surface is frozen. Life survived the ice ages multiple times, partly because water is strange enough to freeze in the wrong direction. Then there is the dissolving. Water dissolves more substances than almost any other liquid. This is a direct consequence of its polarity. Polar molecules interact strongly with ionic compounds, pulling the positive and negative ions of a dissolved substance away from each other and surrounding them, keeping them in solution. The list of things water can dissolve includes virtually every ion and molecule that living chemistry requires. Sodium, potassium, calcium, phosphate, the gases that organisms need to exchange with their environment, The organic molecules that carry genetic information and catalyze biochemical reactions. A cell is, at its most fundamental level, a bag of water with things dissolved in it. The chemistry of life is the chemistry of what happens when specific molecules are dissolved in water at specific concentrations in the presence of specific energy sources. Take the water away and the chemistry stops. There is no dry version of metabolism. There is no alternative solvent that does what water does at the temperatures where carbon-based chemistry is stable. Water is not where life happens. Water is how life happens. And in the early ocean, in a world that had just received 4 billion years worth of volatile delivery and was covered in a warm, chemically rich sea in contact with hot volcanic rock, the conditions for something interesting were assembling themselves. Think about a hydrothermal vent on the floor of the early ocean. Seawater seeping down through cracks in the seafloor, encountering hot rock at high pressure, dissolving minerals from that rock, picking up iron and sulfur and phosphorus and the other elements that biochemistry requires, rising back toward the seafloor, superheated, carrying its dissolved cargo, mixing with the surrounding seawater at the vent opening and precipitating minerals as the temperature and chemistry changed abruptly. These are not exotic conditions. They are simple chemistry. Hot water dissolving rock and rising through it. The same process that drives hot springs and geysers on the surface, except happening underwater at pressures and temperatures that concentrate the chemistry in ways that surface conditions cannot replicate. Today, hydrothermal vent systems on the deep ocean floor support entire ecosystems that have never seen sunlight. Bacteria and archaea that extract energy from the chemical reactions between vent fluids and seawater, tube worms and shrimp and fish that live on those microorganisms. Complete food webs running on geochemical energy rather than solar energy, insulated from whatever is happening at the surface. Independent of photosynthesis in a way that would have seemed impossible before we found them. These vent communities are not living fossils. They have evolved continuously, like everything else. But the metabolic strategies they use, extracting energy from the reaction of reduced compounds with oxidized ones, harvesting the electron transfer that happens when hot, chemically rich water meets cold oxidized seawater. These strategies are among the most ancient in biology. The organisms that sit at the deepest roots of the tree of life, the lineages that diverged earliest from the common ancestor of everything alive today, are almost uniformly adapted to high temperatures and chemically extreme environments. Thermophile, hyperthermophiles, organisms that require temperatures that would kill any organism you would recognize as familiar. This pattern in the tree of life is not proof of anything. Evolution is complicated, and the deepest branches of the tree have been shaped by 4 billion years of change that we cannot fully reconstruct. But the pattern is consistent with something, consistent with the first chemistry that organized itself well enough to replicate, doing so in an environment that looked something like a hydrothermal vent. Warm, chemically rich, energetically active, protected from the violence at the surface by miles of water above, supplied with exactly the elements that biochemistry requires, delivered by the same geological processes that were building and reshaping the planet from below. Water made the vent possible. Water dissolved the minerals the vent needed. Water provided the temperature gradient that drove the chemistry. Water was the medium in which the first replicating molecules, whatever they were and however they assembled themselves, found each other. The origin of life is one of the genuinely unsolved problems in science. We do not have a complete chemical pathway from simple molecules to self-replicating ones. We do not know exactly when it happened or precisely where. We know it happened because we are here. and the evidence in ancient rocks suggests it happened quickly. Within a few 100 million years of conditions becoming even approximately stable, which implies that whatever the process was, it did not require extraordinary luck or extraordinary time. What it required was water, not as a passive background, as a participant, as the solvent that kept everything dissolved and mobile, as the medium that transmitted chemical gradients from place to place, as the substance whose polar chemistry made the hydrogen bonds that hold DNA in its double helix and fold proteins into their functional shapes and anchor molecules to membranes in exactly the orientations that make membranes selectively permeable rather than just barriers. Water did not make life possible the way a stage makes a play possible. Water made life possible the way grammar makes language possible. It is not background. It is structure. It is the rule system within which the chemistry of life is written. Everything that followed, every cell that divided, every organism that evolved, every species that appeared and disappeared over 4 billion years of biological history, every forest and ocean and ecosystem that has ever existed on this planet, was downstream of the moment. Water first sat still long enough in the right place with the right chemistry around it for something to begin organizing itself. Water was not just an ingredient. It was the condition that made everything else mean something. Press 2 fingers against the inside of your wrist. Feel that pulse, that steady, rhythmic pressure. Your heart pushing blood through vessels so small that individual red cells have to squeeze through the narrowest passages in single file. That pulse has been running since before you were born, since the first weeks of your existence, when your heart was barely a cluster of cells that had learned to contract in rhythm. And it has not stopped since. That pulse is mostly water. The blood moving through those vessels under your fingers is approximately 90% water by volume. The heart pushing it is 73% water. The brain generating the signal that keeps the heart beating is 73% water. The lungs pulling in oxygen to feed the whole system are 83% water. Every organ doing its specific job in the machinery of keeping you alive is mostly water in the literal chemical sense. Water that the molecules of life are dissolved in, suspended in, carried by, structured around. You are not a creature that contains water. You are a creature that is water, temporarily organized into a shape that can think about being water. 60% of your total body weight is water. In an average adult, that is roughly 42 liters cycling through your body continuously, never staying long, moving in and moving out, replaced and replenished in a turnover. That means the water in your body today is not the same water that was in your body a few weeks ago. You are not a fixed container. You are a place water passes through. Every reaction in every cell in your body happens in an aqueous environment. Enzymes, the protein machines that catalyze the biochemical reactions keeping you alive, are folded into their functional shapes by the interaction between their amino acid chains and the water surrounding them. The hydrophobic regions fold inward, away from the water. The hydrophilic regions fold outward, toward it. The shape of every protein in your body is determined in large part by its relationship to water, and the shape of every protein determines its function. DNA is stabilized by water. The double helix is held together partly by hydrogen bonds between the base pairs on the inside of the structure, and partly by the way water molecules interact with the sugar phosphate backbone on the outside. Remove the water, and the helix does not maintain its shape. The information it carries cannot be read. The sodium and potassium ions moving in and out of your neurons right now, generating the electrical signals, carrying the meaning of these words from your eyes to the parts of your brain that process language, are doing so through water-filled channels in the cell membranes. The thought you are having right now is a water-mediated event. Now, follow the water backward. The water in your body came from what you consumed. What you consumed came from rain and rivers and the hydrological systems that moved water from where it fell to where you could drink it. The rain came from the ocean, evaporated by solar energy and carried inland by atmospheric circulation. The ocean has been accumulating and cycling water since the first ocean formed roughly 4 billion years ago. Some of that water gets subducted on tectonic plates, carried deep into the mantle, and released again through volcanic activity millions of years later. The water cycle you learned about in school is the surface expression of a much deeper cycle that involves the whole planet, that has been running since the first ocean formed, that connects the water in your glass to the water in the deepest parts of Earth's mantle. There is no clean boundary between the water that is currently in the ocean and the water in the rock below it, and the water in the atmosphere as vapor and the water in your body. They are all in the same cycle, at different stages, and the cycle has been going on for longer than any life on Earth has existed. The hydrogen atoms in the water in your body are very old. Hydrogen is the simplest element. Assembled in the first minutes after the Big Bang, 13.8 billion years ago. The hydrogen that became part of the molecular cloud that formed our solar system has been hydrogen since long before there was a sun to warm it. It was hydrogen in whatever objects carried it to Earth, whether those were carbonaceous asteroids or the mineral building blocks of the planet itself. It has been hydrogen for almost the entire age of the universe. Right now, some of those hydrogen atoms are in the water in your cells, participating in the chemistry that is keeping you alive. The oxygen atoms are younger. Oxygen had to be forged inside stars, in the nuclear fusion reactions that power stellar life and distribute the products through supernova explosions when stars die. The oxygen in your water was made inside a star that no longer exists, scattered into the interstellar medium when that star ended, gathered up by the molecular cloud that collapsed into this solar system. Your body is made of material older than this planet. The hydrogen is Big Bang material. The oxygen is stellar material, forged in a nuclear furnace that burned out before the sun existed. Together, bonded into the bent polar molecule that makes everything in this story possible. They have traveled from the first minutes of the universe to your bloodstream through a sequence of events spanning 13 billion years. Every water molecule in your body has a history that begins before this planet existed. You have been wondering, through this entire story, where the water in your glass came from carbonaceous asteroids, possibly from the hydrogen locked in the mineral structure of Earth's building blocks, possibly from a combination of sources accumulated over hundreds of millions of years of bombardment and outgassing and geological cycling, probably. But here is the question underneath that question. If the hydrogen in your water is Big Bang material, and the oxygen was forged in a dead star, and those molecules arrived on this planet through a process spanning billions of years, and they are right now inside you, participating in the chemistry that constitutes your existence. Where exactly does the universe end and you begin? There is no clean line. You are a local and temporary organization of matter that has been here since the beginning, arranged by 4.5 billion years of planetary and biological history into a shape that can ask questions about its own origins. The water in your body is not a resource you are using. It is the universe, passing briefly through a human form. Pick up the glass again. Same glass, same water, same transparent. ordinary, unremarkable liquid sitting in your hand the way it has every time you have picked it up for your entire life. But you are not the same person who picked it up at the beginning of this story. You know now what it took for water to be here. The planetary violence it survived. The delivery that happened not once but continuously. Over hundreds of millions of years. From sources we are still working to fully identify. The fact that two neighboring planets received the same delivery and could not keep it. And that the reason this planet kept it comes down to a set of properties so specific that nothing else in this solar system has replicated them. You know that the water cycling through your body right now has been inside this planet since before the first ocean formed. That it has moved through creatures that lived and died before there was anything complex enough to have a name. That when it leaves your body, as it continuously does, it will return to the same cycle and continue moving through it long after you are gone. There is no moment when the water in that glass stopped being part of Earth and started being yours. There is no moment when it will stop being yours and start being something else. It is all one thing, moving, right now, for just this moment. It is yours. Drink it.